Today with me is Mijndert Van der Spek from Heriot-Watt University, and we're going to speak all things related to direct air capture. So it's a process or a set of technologies that literally takes CO2 out of the thin air and tries to make use of it, right? So we try to either utilize it or store it to support the negative emissions agenda. So the structure for this is we're going to do a brief career-related Q&A at the very beginning for your benefit. And then we're going to talk about the core subject, direct air capture. There will be opportunities for you to discuss direct air capture with us, with Mijndert, at the end of this presentation and this discussion. But as I mentioned at the very beginning, I do invite you to engage. So if you've got a question, raise your hands up or leave your comments, and we're going to answer all of them, hopefully within this hour. If not, we're going to follow up after the session. So without further ado, welcome everyone. I want to ask you, Mijndert, can you introduce yourself a little bit and tell us what do you do in your daily life?
Too much and not enough. Okay, yeah, very happy to be here. Welcome to everybody. So my name is Mijndert Van der Spek. I am an associate professor at Heriot-Watt University, located in Edinburgh, Scotland. And I'm also the associate director for technology and systems assessment in the Research Center for Carbon Solutions, which is one of the research centers here in the university. I've spent about a decade researching CO2 capture, utilization, storage, and about 6 years of direct air capture now, I think 6-7 years. And I'm very excited about direct air capture, not because it's the silver bullet that's going to solve climate change, because there is no silver bullet that's going to solve climate change. There are many small pieces together that together may contain a bullet to shoot a hole in this problem. But I think it's a fascinating technology, just as a technology enthusiast, and I also do think there's a lot of potential. Was this enough for an introduction, David?
Yeah, that's really great, and I'm happy that you emphasized that DAC is not silver bullet, but we still need this at some point in the future.
Well, not only in the future, David, but we can have a longer chat about that.
We can have a discussion about this. Right. So how did you get involved in CCUS in the first place?
Yeah. So I think all through my undergraduate studies that there were, topics in my studies that focus on decarbonization and CO2 emissions reduction, things like biodiesel, CO2 capture and storage, electrification, wind energy, all these kind of things. So I found that very interesting. I did my master thesis with a company called Shell, and that was on making biogas from biomass with the technology that people in Dan Janssen's team had invented, at then called the Energy Research Center of the Netherlands, but that was biomass gasification technology. And then I investigated a process to make substitute natural gas from that, so bio natural gas. And then I stayed at Shell for a couple of years and I realized a number of things, why that may not be the career path for me. So then I joined Utrecht University for a PhD degree, and I just, while chatting with the professors there about possible topics and projects that they have, this one I found particularly interesting because it was close to what I knew as a kind of a systems engineer, but also because it made a real impact, or at least to my mind, that it would make a real impact to decarbonization.
That's really exciting.
Yeah.
Really,
so I got in and never left.
And industrial expertise, really.
Well, but it helped a lot. It helped a lot with, and the nice thing about that first PhD project was that there was a heavy involvement of industrial partners. And funny enough, I had nothing to do with that, but Shell was one of them again. But there was also Siemens was involved, and an Indian oil and gas company called Bharat Petroleum. And it really helped that I had 3 years of experience to understand how these companies worked and what matters to them. Not that I always agree with that, with their priorities and methods of operation, but at least I knew where they came from and what kind of language they spoke, right? And that really helped in my communication with our industrial partners.
It's really great. And in terms of looking to the future, I know we talked about CCUS for the past 20 years. It's finally starting happening. DAC is it starts happening as well, because we can see those small scale units, not that small with the Climeworks, but they are coming up. What are the career opportunities for people to get involved in that industry and research?
I think loads, and that's really good. So what you see now is when I started, we hadn't been building very large installations yet, although the first ones were kind of coming into a detailed planning, detailed engineering stage. But it also meant that the community, the global community, was still quite small, and most people kind of knew each other, right? That is certainly not the case anymore. And I think what is very nice to see is that the whole CCUS kind of moved away from just an academic exercise or something that policymakers would talk about in positive or in the negative sense, into knowledge that's being embedded in large corporations and small corporations. So there are career opportunities really in many engineering firms, I would say, also in policy making, many NGOs that are involved in this. And interestingly, also many startups, right? So many people start a new venture, and we didn't see that much. We didn't see so much of that before, especially in CCUS, because carbon capture from industrial flue gases, for instance, because it always involves very large scale processes that need a lot of expertise and project management expertise, and especially project realization expertise that usually resides in very large companies. And one of the nice things about direct air capture is that it can start at a slightly smaller scale and you see a lot of enthusiasm. So I think at the moment there are more than 160 direct air capture companies in the world at different stages of development. They all claim to have a unique technology, which cannot be true by definition if there are 160 of them. But at least it shows a lot of enthusiasm. And I think that enthusiasm is something that is very characteristic of carbon dioxide removal in general, but also for direct air capture.
And you need that innovation to make it happen, really.
Yes, and and innovation doesn't only happen in universities. That's a complete misconception. Innovation happens in companies and research institutes at the same time. So
yes, definitely. And in terms of how people can get involved in research within direct air capture space, what are the main topics that are being researched right now?
In direct air, there's so much going on, and if you aspire a research career, then usually it's necessary to have a PhD. So that goes for research in companies as well as research in startups and in academia. So it's not a bad start to go and do a PhD in direct air capture materials or processes or technology evaluation. At the same time, that doesn't mean that you have to stick to academia to work on direct air capture research. And as I said, the funny thing about direct air capture is that because there are so many companies, most of the technical knowledge resides in companies and not per se in the public domain. So in the work that universities disseminate. So we're always one step behind, or maybe even 10 steps behind what the companies do. And that's frustrating. And on the other hand, I also find kind of I find pleasure in trying to unravel then what they are doing and trying to bring some of that information into the public domain.
Trying to understand how their process works and what materials potentially they can use, because they're very protective for valid reason about the IP. That's as you said, there is opportunities both in academia and in industry, especially startups right now. But looking at where that startups are recruiting, that's mostly around process engineering, around research engineering. So those are the topics and career titles that people will be looking for if they want to get involved in that space. We've got a couple of questions ready, but we're going to discuss them at the end, which is really good. So if you've got any questions, leave them in the chat. We're going to catch up at the end. So that was really helpful, and I think that gave people an overview of where you came from, what was your journey, and why careers in CCUS and particularly DAC could be very exciting because it's a new technology that could, it would help us decarbonize and achieve net zero. Do you have a couple of slides about DAC?
I would have, yes.
Yeah. So if you don't mind sharing them with people on the call, that would be really great.
Okay.
And I'm really happy to see so many of you joining today. Very happy.
I think easiest probably is to share my entire screen. Is it correct?
That's the easiest way. Yeah.
And that is what I'm going to do. Then I will, however, close my email.
Close anything confidential.
Sorry?
Close anything confidential.
Yeah, exactly. So I'll close my email
Yeah.
to make sure that not that the whole world can be with me. Okay. So when David invited me for this lecture or webinar, I chose the title "All You Need to Know About Direct Air Capture from Technology to Socioeconomics and Everything in Between." And of course I was bluffing because I don't have time to discuss everything in between, but at least I can discuss some things. And the reason why I chose this title, but also the work that I'm going to show, is because we, and then I mean a group of 25 people that I think about 25 people that I will show at the very end, are doing a review of the complete direct air capture and storage literature at the moment, and that literally means we try to review every and any paper. Now we are lucky because as per end of 2023 there had only been 800 papers published, so that's not too many. Similar reviews are happening for other carbon dioxide removal strands, and some of these people are a little bit less lucky. So for instance, on biochar there's a massive body of knowledge that spans about 30,000 papers, and all of these have to be coded by hand, which of course didn't work, so they're now moving to kind of a different reviewing exercise. But so we're lucky, but I expect at least 400 more papers till the end of 2024, so let's see where we get to. So what is direct air capture, and does this exist yet? And the answer is yes, it exists. It's not a myth, or it's not something for the future. It is happening right here and now. And what it does is that it captures CO2 molecules directly from the air to permanently store it or to use it. And I think it's important to realize that capturing molecules from the air is one thing, but then something else needs to happen with it, right? So I put two pictures on the screen. One is of the Climeworks Orca plant. This one was opened in Iceland in 2021, and then earlier this year the Climeworks Mammoth plant opened, which is approximately 10 times larger, also in Iceland. And the reason why in Iceland is because there is kind of free waste heat available from geothermal sources. Maybe some people know that there is a lot of what they call geysers. The word geyser comes from Iceland, like hot pools, and that's all because there's a lot of heat in the relatively shallow subsurface that can be used. And because Iceland is so volcanically active, there's a lot of basaltic rock there, and basaltic rock is very good for storing CO2 because it's very active. It has a lot of minerals that actively react with CO2 to form, for instance, calcium and magnesium carbonate, and that's a permanent form of CO2 storage in solid form, so in a rock, so it can never be released again unless you heat it up to 900 degrees C. So The current capture volumes are actually small, while the first 500 kiloton per year plant is under construction at the moment in the USA. So that's going to be sizable. Just for reference, a typical cement plant will emit CO2 emissions in the order of 500 kilotons per annum. Some cement plants a bit less, some a bit more, but that's approximately the ballpark. And then the question that always pops up is why do we need carbon dioxide removal? And I tend to use these figures from the IPCC special report on 1.5 degrees, but I must admit that they're starting to become a bit old. They're about 7 years old now, but they just convey a very nice message. And what you see here on the screen is four different scenarios for future decarbonization. And there are four pathways really, and there are many more, but these are four archetypal pathways to reach 1.5 degrees C at the end of the century. That's always that's always the measurement point. So we want to stabilize the temperature at 1.5 degrees at the end of the century. And what you see in each and any of these scenarios is that after having a lot of emissions, and that's still a situation we're in now, unfortunately, around mid-century, so 2060, 2050, something around that time, somewhere around that time, we will need to reach what is called net zero. And that means that on a net basis, we emit zero CO2 emissions. Now, you cannot emit zero CO2 emissions because human activity, be that agriculture or transport or industry, will always emit some greenhouse gases. That's inevitable. Think only, for instance, of the fertilizer that we put on soils. That emits nitrous oxide, dinitrogen oxide. So and that's a potent greenhouse gas. Cows emit methane from their breath that just comes from their digestion process, right? So that's something that is very different. It can be, you can reduce the amount of methane that they expand, but you can't reduce it to zero because it's inherent to their digestive process, and we have a lot of cows in the world. The same with some forms of industrial activity. So what these figures show is that in any scenario that leads to 1.5 degrees, and the same goes for a 2-degree scenario, some form of carbon dioxide removal is needed to offset the carbon emissions from hard to abate industrial activities, and then to become net negative, so to remove CO2 that we have emitted to the air before, let's say, the net zero point, because just getting to net zero is not enough. So you see here the gray lines here, they show the netto CO2 surplus or drawdown that needs to be realized in each of these three scenarios. And you see that in each of the, four scenarios, and you see that in each of them, the netto line goes to negative. So that is why we need carbon dioxide removal. So we need to decarbonize our industries massively and drastically, and our transport and everything else, our agriculture, but that won't be enough. So we need carbon dioxide removal in addition to normal decarbonization, not as a substitute to normal decarbonization. And this was something that I was talking about just before. So this is just a slide showing how the literature on direct air capture is growing exponentially. That this started in about the 1990s. There are very few papers, and in the last couple of years it's going up really, right? So you see more than 200 papers per 2022, and they're kind of evenly distributed over materials, process design, and integration. Interestingly, these very early papers, they're really only about DAC in space stations or in submarines, because at that moment we didn't need to remove CO2 from the atmosphere, but we needed to remove it from enclosed spaces, because otherwise you basically pollute the environment that astronauts or Navy crews are operating in. So just a little bit about technologies, and what kind of technologies exist. And as part of the review, we identified approximately 9 technology combinations. In an earlier paper, we had 10, but it doesn't really matter. It's roughly the ballpark size. So you could look at solid adsorbents for direct air capture, liquid sorbents with calcium looping. You can look at amines and amino acid salts, which is something we know very well from regular CO2 capture. There's a lot of interest in electrochemical CO2 capture and then regeneration, so you can distinguish between solid electrochemical and liquid. Mineral looping is a very potent way of removing CO2 from the air. And then there's membranes, and in the bottom there's cryogenic. Now, what is probably interesting to realize as well is that, if you look at what we call technology readiness levels, so how close is a technology to commercialization, and where 1 is, basically there's nothing yet, only some initial concepts and principles have been formulated, and a level of 9 means it has been deployed in a real operating environment at the scale that it should be deployed. You see that there's a large variation between those technologies. So for instance, cryogenic is at 1 and will probably never go further because of something I'll show later. Solid sorbents is at 9. So is mineral looping, because commercial plants have been built and are operating with the CO2 being sold. So, to me, that's a definition of commercial. If you're earning money with it, or if you're selling your product, then for me, that's commercial. 3 plants have been built for solid sorbents and 1 for mineral looping, but the maximum size is still only 36,000 tons per year, right? So that's very small. But I said before, a cement plant emits about maybe half a megaton of CO2 per year, whereas a decent sized coal power plant, for instance, emits 4 megatons. So this is still a couple of orders of magnitude lower than that. Just have some images here. This is the Heirloom Uno. So Heirloom is a California-based company that we know very well. They indeed use calcium oxide, or actually calcium hydroxide, to capture CO2 from the air. They use a whole tray-based system. Go onto their website; it's really interesting. And they recently opened their first plant. So this is very small, 1 kiloton per annum, and the capturing actually happens inside this building here. So there are loads of stacks with trays, and those trays all have dust on them, minerals, calcium hydroxide, that capture the CO2, and then robots collect these trays, take them out of the stacks when the calcium hydroxide is spent and converted to calcium carbonate, and then they regenerate that in an electric kiln. So at temperatures of about 900 degrees, but fully electrically driven. Here's an artist's impression or a rendering of 1.5 Stratos plant. So this one is to open in 2025, and this is about half a million tons per year. So this is the first really big one, and their last press release said it's about 70% complete. So this one is going to be really big, and it's almost done. It should be opened, commissioned, and started up next year. And then this is an image of carbon capture, which is another company that is really moving fast. The contactor is called the Leo series. Give it a name. This is 1 module, and they're going to use this in Project Bison in Wyoming, and they aim to have a 1 million ton per year site running by 2030. So they're going to use that by just replicating this one. Sorry, they're going to do that, but just replicating this one module. So they're going to build heaps of this one module to reach the 1 megaton per annum. So yeah, maybe a couple of take-home messages about the technology, right? So we need carbon dioxide removal and direct air capture to reach agreed climate targets, but that's additional to deep CO2 mitigation and not instead of. There's roughly 9 technology categories spanning different air contacting and regeneration mechanisms. The current technology readiness level ranges from about 2 early lab to 9 commercial. And there are 3 DAC plants that exist and operate. One of the 4 has been shut down already. Again, I mean, you know, simple. It was end of contract for the CO2 delivery, and there are 2 more under construction. And I'm realizing now that I may forget one plant that Global Thermostat built in Hawaii that's also actually operating. Maybe let's have a look at DAC's performance. And I think, you know, I always start with this slide, and it's a very nice slide by colleagues from the Professor Institute and ETH in Zurich. Tom Terlouw is his name. He happened to study in Utrecht, so I have a nice connection with him. But it is really a system, so it's not just the direct air capture unit. And what you need first and foremost is heat provision, because a lot of these DAC technologies, they need heat to regenerate either their sorbent or their solvent and release the CO2 in a pure form after it has been captured with a sorbent or solvent. What it also needs is electricity provision, so that's also very important. And you see here in this box, you see energy conversion, and then it says HTHP, which basically means high temperature heat pump. So you can also provide the heat by electricity. And that's a route that many companies are taking, because you can decarbonize electricity much easier than you can decarbonize other forms of heat. And then at the very end of the value chain is, of course, CO2 compression, transport, and storage. So once you have produced pure CO2, then you need to compress it to 110, 150, maybe even more bars, and you need to transport that by pipeline or by truck or by ship to wherever it's going to be recompressed and then injected into the ground. So I'm here obviously assuming that it's going to be stored and not used. And by the way, we really need to store it in order to be net negative. And the amounts that we need to store are much orders of magnitudes larger than the amounts that we can use to make, for instance, fuels or something else. And then finally, just, you know, out of this whole system diagram, there's only one block that says DAC operation, and then there's some other things like production of the DAC plant, dismantling, sorbent production, etc. But I think it's important to realize that DAC does not, you know, it's not just a unit. It includes a whole system, and that whole system needs to be integrated and needs to be present for the DAC to be able to operate. Now here come a couple of difficult graphs, and I will take some time to explain them. But here we're going to look at energy consumption. And what we've been doing is we've been gathering energy consumption data from the body of scientific literature out there, or I should say peer-reviewed literature. So we include everything that's peer-reviewed, published in scientific journals or else. And what we're showing here is the total electricity requirement, and that's in gigajoule per ton CO2. And you see that on this axis here. And then here on the horizontal axis, what we show is the date of the publication. So you see that some of the first publications were early 2000s, but actually there was one already in 1999 that I'm not sure why it doesn't show up, but you know, we're not completely done. And then what you see here is something, you basically see the kernel density estimate. So how many of the points fall at which, you know, total electricity requirement level. So what we've done to compare technologies that are driven by heat and technologies that are driven by electricity is we needed to harmonize that, right? So for high temperature heat, and then I mean 900 degrees, for instance, like for solvent-based DAC, we assumed that could be supplied by an electric boiler with a coefficient of performance of 1, which basically means 1 gigajoule of heat equals 1 gigajoule of electricity input. Of course, it's a little bit less than that, or sorry, a little bit more in reality, because you never have 100% efficiency from electricity to heat. But that's what we assumed here. It's a fair, you know, it's a fair assumption. Usually these efficiencies are above 90%. And then for low temperature heat, so for instance, sorbent-based DAC, we assumed that that was supplied by a heat pump with a coefficient of performance of 2. And then some insights. And I think the first insights are that the ranges are massive. right? And you see some point estimates here. You see them all across the map. You see some very high ranges already early on, and you see some very high ranges later on. And this basically means that, that there are very large ranges. And if you want to have an efficient direct air capture process, you really need to optimize the material, process, and heat integration combination. So these three elements. What we also see is that, there isn't necessarily a clear winner, although if you would drive solid sorbent-based direct air capture with heat pumps, you may take from this graph that maybe that has the lower energy requirement, at least lower than solvent-based technologies. I'm not saying per se whether that is true or not, but this is what the literature suggests. What we also see is that there's only one study on membranes, this orange line here, and the energy consumption of these membranes is very high. And by the way, they only render then a 50% pure CO2 stream, whereas all the other ones render a very high CO2 stream. Now, this is also interesting. Some of the points reported in the literature fall below this dotted line, and this dotted line is the minimum theoretical work needed to take CO2 from the air and purify it to a 95% pure stream, and do that for 50% of the CO2 that is present in the air, right? So you take 50% out and you purify that to 95% purity, and this is the minimum theoretical work, and some of the report points fall below that line. So clearly the people who reported that haven't done their homework so very well, because this is thermodynamically impossible. And it also says something about how careful you need to be with interpreting results that you find in scientific study, and especially all the nonsense that you hear on the internet about, how good DAC can be. I think a lot has been said and written about that, but always keep your eyes open to what may and what may not be true. And then very finally, and this is why I don't think cryogenic direct air capture will ever move beyond TRL1, is that there's this lone star at 30 gigajoules per ton captured, which is really a lot of energy, and that is cryogenic DAC. And this was under the best of conditions that you can find on Earth or on Earth. So in winter in Alaska, if it would have been in summer in Alaska, then it would have probably been double the amount of energy. So let's forget about that one. Oh, I have here energy consumption, but what I mean is that the cost also varies enormously, and this is still work in progress. So we have quite a few more references that we still need to put in, but it's kind of a similar graph where we try to harmonize all the cost data that has been published, so over time, onto the levelized cost of net CO2 removed, so dollars per ton. And the harmonization that we did is all costs are in US dollars. They were all converted to 2023 values, and they all include CO2 transport and storage. And therefore, we were able to present the levelized cost of net removed. And here the insights are very similar. So, the ranges are large. One point is close to zero. That's this one here. How realistic is that really? Well, the answer is it isn't. And then adsorbents and solvents have overlapping costs. So there is no clear winner there. But it also, if you look at this, this also raises the question whether or not $100 per ton per ton CO2 net removed is really a realistic target. And I'm mentioning this because that's the target that the US DOE is aiming for. And then people say, yes, but how about DAC 2.0 and DAC 3.0, and how is it going to be in the future? And interestingly enough, we did a study into that ourselves. So we were very keen to understand where the cost may be heading, and so we projected the cost using technological learning and etc. for 4 technologies. And again, what you see is that the ranges and uncertainties are very large. That's normal because it's very difficult upfront to say how much something will cost exactly. And what you see is that all the technologies mainly reach a similar cost level that we estimate to be about $100 to $600 dollars per ton net removed. And that is at the gigaton scale. So the 10 to the third is 10 to the third power of 3 megatons. So at 1 gigaton, we think that direct air capture will cost $100 to $600 per ton. And luckily, there was a study that followed up not followed up, but that did kind of similar work to what we did, and they found the same. So this is a study from ETH in Zurich, and they said that long-term costs would be between 200 and 300 US dollars per ton net removed. So that also includes transport and storage again, right? And they also suggested that most technologies will reach similar cost levels. So that means a couple of things. So yes, we can reach much lower cost. Maybe $300 or $200 per ton is feasible. It also means that all these people that claim that they can do below $100 per ton, that's just marketing. That's probably not true, and they should know that, but they don't always know, because they don't realize yet how difficult it is to build a real plant, and how costs are going to escalate really quickly when you try to develop something in the real world compared to what you have in the lab. And I think maybe the next quote is a good example of that. So, finally, after years of speculation, Climeworks has given what they think are the costs for solid sorbent direct air capture, and they made that information available during the CDR summit that they organized earlier this year. And they say that now in 2024, they estimate solid sorbent DAC to be about $1,400 US dollars per ton, 1,400. And by 2050, it will be 250. So no 100. And then still there are companies that say we can do better, and maybe they can do marginally better, but they cannot do massively better. And the only reason why they can make that claim is because they don't know yet what Climeworks has gone through, and what Oxy has gone through, and what Carbon Engineering have gone through, and what Heirloom have gone through. So the only people who really know what it really costs is the companies that have built or are building a real plant. Right? So I think that's an important learning point. Don't believe everything don't believe the marketing always. Still, direct air capture will be very important. And then finally, this is a question of siting. So, there may be sites that are more or less beneficial from a cost perspective. So what we see is that costs are generally lower in China, and they're generally higher in Australia. That has to do with energy price, the cost of labor, the availability of trained engineering crews and construction crews, etc. And another learning point is that hydro energy is the cheapest form of energy to power such plants. So that works best. Intermittent renewables, not so very good. Non-intermittent renewables could be better, but you cannot operate a direct air capture plant at 50% or at 30% of its maximum capacity, because then you have to invest an enormous amount of capital that you then don't use, so you can't amortize it over CO2 produced or sold. Okay, I think this is the final slide on performance, and this is about environmental assessments. And it's again a bit of a difficult slide, so I'll take a little bit of time to explain it. But this is all LCA material. So our co-workers Bolangaro and Dufour have compiled this from the available LCA literature, and they included the studies that were complete and that could be reproduced. So there are more LCA studies, but they aren't complete and/or cannot be reproduced. That also tells you something about the quality of the scientific literature sometimes. And what you see here on the horizontal axis is the greenhouse gas intensity of electricity for CO2 capture, right? So that is kilogram CO2 equivalent per kilowatt hour of electricity. And then here you see some country names that this equates to. So for instance, Switzerland has a very low CO2 intensity, Iceland too, Denmark comparatively low, then Portugal, Italy, and Germany is especially bad. Boo, Germany. very high CO2 emissions per amount of kilowatt hour produced. And then what you see on this axis is the climate change impact of CO2 captured from air. So of course, when you capture CO2 from the air, you also emit CO2 because the energy that you use, because of resources that you use, and so on and so forth. And what you see here is basically a measure of the net removal, or actually rather maybe on this right axis, they displayed that as an eta CO2, which is the removal efficiency. They did a lot of harmonization of all these studies, so they calculated the values again completely for all the studies included, and they include the full value chain, cradle to grave. For high temperature heat, they assume it's supplied by natural gas, and for low temperature heat, they assume it's supplied by a heat pump. Okay, so one of the first insights is that there's only 5 LCA studies that can be reproduced. So that's not many. I'm aware of a new one that was published last month, which is probably pretty good. So we still need to add that. And the LCAs are only for classical adsorbent DAC and for solvent DAC. So here come the lines. And you see that the different studies, they change with the CO2 intensity, except for this one by I think it's Enric Prat-Salvado, because they assume that all that electricity is generated within the DAC machine, which for that process can be true, and that they don't have to compress the CO2, so they don't have to buy any CO2 from outside. Let me have a look. So what we see is that all the direct air capture studies, LCA studies, indeed show negative emissions, right? Net negative. So they all have a removal efficiency lower than 0, except this orange line here that at some point becomes net positive. But that's because it's an example of a very small direct air capture plant. They did it for the Orca plant. And it's not very representative of large plants. But it also shows that if you go to, for instance, the grid intensity of Germany, then your net removal efficiency is only about 40. So of all the CO2 that you pull out from the air, out of the air, 60% is re-emitted again, for instance, through energy generation. And these kind of things are really important to show people, policymakers also, or especially what DAC can and cannot do, and what it needs, right, to be really net negative. Okay, so a couple of take-home messages on performance. So the energy performance varies and is still uncertain, and it depends a lot on heat integration as well. And I expect that 5 gigajoule per ton captured in terms of electricity or work is certainly feasible, and it may likely be a bit lower. So 4 or 3 would definitely be possible too. The cost of direct air capture are still high, but they will fall to $100 to $600 per ton CO2 net removed by about mid-century. So that's we have to wait for another 25 years for that. Before that, it will be substantially more expensive. The cost will come down due to repeated deployment, mass production, and learning. And finally, rational siting helps identify optimal / cheapest spots for direct air capture deployment. Now, I hope I didn't bore you to death yet. There's a couple of more slides, and we're switching gears now to some of the socioeconomic considerations, because, with carbon dioxide removal, as with any new technology, but also, any industrial activity, socioeconomic considerations basically give the constraints and the boundary conditions in which it needs to operate. So if people don't want it for whatever reason, then it may well be that it won't happen, or it will happen in a manner that is irresponsible. And that's why social and socioeconomic considerations are really very important. And one of the things that you can do then is look, for instance, at equity and justice dimensions. And this is a study, done by Benjamin Sobakov and his teams, and it looks at the perceived or the real potential negative equity and justice impacts of direct air capture. And I want to stress the perceived or real, because this is just by asking people, and it doesn't necessarily need to be true. And I say potential. So again, it doesn't have to, it doesn't have to be the case. But as an example, if you look at the first row here, that's about resource extraction, chemicals, and fertilizers. Then the perceived or real negative impact is that of the affiliated mining and material needs. So if you're going to do an industrial activity like direct air capture will be, you need to extract minerals and materials, right? And concrete can be one of them. People may be worried about the chemical pollution from solvents or from absorbents or adsorbents, and that's something that you need to manage really carefully. So of course you need to make sure that your direct air capture plants don't have adverse externalities, adverse additional effects on people and on communities, especially not on their health. On the manufacturing and the labor and the ownership, there may be a resource curse risk for workers and communities. So that also again relates to how are we going to treat the people that have the resources? Are we going to treat them equitably, or are we going to do things like land grabbing and just making them work to mine materials for us at very low wages in terrible conditions, right? So there's really the way that we do it will determine kind of the social license to operate for direct air capture. The creation of sacrifice zones near deployment and also the strengthening of fossil fuel incumbents when coupled to enhanced oil recovery. So there is a large perception that direct air capture allows fossil fuel companies to continue to produce oil and gas for longer, which isn't necessarily true. I don't want to go through all of them. You can probably read them in the forthcoming paper or have a look at the recording later. But I think it's important to understand that there are concerns about equity and social justice when it comes to carbon dioxide removal and direct air capture. Now, really focusing more on the public perceptions, and this is all done, information that comes from surveys, from focus groups, so from asking real people, is that DACs is viewed mostly positively, and there's no significant controversy. So much less than with biomass, for instance, where that means monoculture plantations. But at the same time, the perceived risk may be a little bit higher than for other CDR, carbon dioxide removal verticals. And the perceived benefits may be a little bit lower. So there's a perceived lack of naturalness because it's all completely engineered. What people really like in the CDR space is kind of the agriculture and the forestry methods, right? So use agriculture to draw down more CO2 because people think that sounds natural to them, and for good reason that they get good feelings from that. There is also perceived tampering with nature going on there. There's some concerns about the safety, reliability of geologic CO2 storage, and there are some controversial associations between DACs and the fossil fuel industry, as I highlighted before. And then a final finding is that there is generally stronger support with stronger sense of climate urgency and more obligation to climate change. That means that people who really understand the scale of the climate problem, they tend to be stronger supporters of CDR in general and DAC in DAC specifically. And the reason is because other people don't understand really, or they because they don't know, or they haven't been told that we need to remove CO2 from the atmosphere to actually meet climate targets. Many people still think that building a couple of wind turbines and building a couple of solar PV panels will solve the climate emergency, and that really is not the case. But it's people are not very well informed, and not through any fault of their own. But we as a scientific community can probably do a little bit better there still. And then finally, and this is really important, especially for early deployments, there are what I call here socio-geographic sweet spots for direct air capture and storage. And that means that some areas just have it all. They have cheap, clean energy. They have the CO2 storage capacity, because mind you, you cannot store CO2 everywhere in the world. That needs a specific geology. They have an experienced workforce, for instance, because there's already oil and gas production going on there, and you know the workforce is very similar to what is needed for DACs. They have low social vulnerability, which means that new activities or new economic activities can be deployed quite easily without disadvantaging certain vulnerable communities, and you know that can be minorities or the less educated or you know the less wealthy. And there's a high amount of energy equity and environmental justice. So people have not negatively, how do you say that? Have not been negatively burdened with previous industrial activities, and won't be negatively burdened with new industrial activities. And this is really important. And for instance, this is a study from the US, this was a very important one. It's called roads to removal, but that basically showed is that here in the north of the Midwest, so North Dakota, South Dakota, maybe Wyoming, that's actually those states can be potential early leaders in DACs, because you know the stars just align in this area, in this region. And then, for instance, here in the west of Texas, New Mexico, Utah, maybe, there's an opportunity for capacity building, and it's a little bit less. So there is a higher what they call social vulnerability index. So there's an opportunity there to reduce the social vulnerability, you know, through direct air capture deployments, if you do it well. So if that goes hand in hand with investments in infrastructure, in schools, in job creation, very important, in lifting certain groups of people out of poverty or marginalization, then there can be an opportunity to do that, but you have to do it really well, because otherwise you just, you know, keep doing the same thing, and only the people who have benefited before will keep benefiting then, but it won't, you know, lift other people into a better position. And this study was done for the United States and for every CDR vertical or CDR pathway, and of course you can do this for the whole world, right? And yeah, I mean it would be a massive task, but you can do it. So maybe some socioeconomic take-home messages then. So there are potential equity and justice risks or barriers, and they need careful management, where equitable implementation should be centered. So the success of the whole energy transition and climate change mitigation will hinge on equitable implementation of solutions. If you forget about people that feel left out already, and that have or that have a disadvantaged position already, then that's like a recipe for trouble. And you know, that's no different for direct air capture. DACs is still largely viewed positively, while a little bit more negatively than other, maybe more natural carbon dioxide removal pathways. And finally, there are social geographic sweet spots for DACs deployment, which may serve early deployment and hopefully will create successful examples for further rollout. And that's again the same, you know, we only have 25 years, right, before we need to reach about a gigaton of negative emissions. So we don't really have the time to muddle around and to do things wrong. So we need to do them right first time. And I think that's really important. So if we have a couple of very successful examples, then that will spark or lay the foundation for large-scale rollout. If we mess up the first time, then we probably set the whole DACs industry back for another 10 years. Very much the same way we've done with CCUS. This is a list of contributors. I think it's indeed about 25. I think maybe a nice note is that they come from all across the earth, and as you can see from their last names, they have very different backgrounds. So that's a really good thing to see. And then finally, this is the slide that I always finish off with, because I really love the picture, but I think the message is important. So if it were to me, then we would all do DACs.
And I agree with that. Thank you very much, Mijndert. That was really interesting presentation, and looking forward to reading this study once it's available. If I don't know whether it's done already or.
We're two-thirds, I'd say.
Okay, so it should be available at some time soon, hopefully.
I have a soft deadline for the end of October for submission.
No, okay.
But I don't think we're going to make that, but who knows?
Yeah, that might take some time until it's peer reviewed. But it's good to see this kind of early preview, and all of you on the call, you can actually see lots of work has been done on that, but lots of work has to be done as well. I really was happy to see that you did siting analysis as well. We did that for one of the energy companies as well, and I don't know whether you looked at the combination of energy, economics and environmental impacts, because that would be quite important. What we saw, usually countries where you have low cost energy, your kind of African countries, Middle East countries, you've got very high carbon intensity, which basically means that it doesn't make sense there now. But from the business perspective, you can justify that low cost of about 200 to 300, 400 right now, with potential decrease, as you mentioned, with the learning curve. So that's really helpful to see. We do have quite a lot of questions, so I'll just start one by one, I think, going from the beginning. So what do you think are the pros and cons between Climeworks and carbon engineering technology? Thank you, Trevor, for this question.
Look, I always advocate the portfolio approach. So I don't think we should focus very much on one technology now. The reason why these two are always compared is because they were the first two to be developed to a pilot and then to a commercial scale. A pro as well as a pitfall for the the carbon engineering technology is that it is natural gas powered for the moment. I'm saying that can be a pro because that may lead to better economics at a short scale in areas where natural gas is cheap, which isn't necessarily everywhere, but there's still parts of the world where it is. It will be a pitfall in the long time or in the long run, because people may not want natural gas anymore and may therefore still how do you say that, compare it so they will see it in relation with the oil and gas industry, which isn't great. At the moment, the carbon engineering technology, I think, is quite a bit cheaper than solid sorbent technology, but it also has much less potential for cost reductions. So and the solid sorbent technology has the benefit that it can be built at a much smaller scale, and that allows for repetition for small scale implementations. That means less financial risk for the investors. It makes a hell of a difference whether you invest 3 billion or 300 million. It makes a massive difference for investors and for attracting investment. So you may be able to do quite a few more repetitions and therefore learn from these repetitions, right? While a technology like carbon engineering that scales, the economies improve with scale, not with numbers, and therefore they need to build immediately at large scale. Yeah. So I mean, it's more in terms of scale up, in terms of engineering, it's more a financial risk. It's more risky. The potential benefit is that it may be cheaper for the coming decade or so.
And at the end of the day, it depends on the project, which technology would go for, depending on the business case and what are the kind of local environmental characteristics.
Exactly, local environmental characteristics as well. Yeah, absolutely. Yeah. So there are many more differences between the two, right? To many, maybe.
Yeah. And naturally, materials play a critical role in DAC, as you explained as well. Is there a scope for doing molecular modeling with AI to identify those materials, or is there any work being done right now?
Oh, there's a lot of work being done. but and a lot. And funny enough, all the big AI companies are also jumping on this because they see that as a massive opportunity. So Meta, I think Google, and a number of other companies. So I have one of my colleagues here, Susana Garcia, is doing she's doing a lot with machine learning and AI and materials discovery, particularly metal organic frameworks. At the same time, this is for a fact, again, not a silver bullet. It is something that may really speed up materials discovery and may lead us into directions that we would have otherwise not gone. But that doesn't mean that you can just train a machine and then let us find things and think that something fantastic will come out of that. The engineering still needs to be there. The experimental testing still needs to be there. You still need to be able to make these materials. But yes, there's absolutely a role, and people are very actively working on that across different companies and universities in the world.
Yeah, and that's applicable to CCS, but also DAC. Lots of research is being done in this space.
Yeah.
I think one thing that we haven't touched in the presentation, and it came up in the questions, why do we, in principle, do carbon capture when DAC is becoming cheaper? And can we do DAC instead of the carbon capture then?
No, absolutely not. And so it's an absolute myth that DAC is cheaper than carbon capture, because it isn't. Anybody who will tell you that is lying or doesn't know his own cost structure.
Yeah,
it's an
Agreed.
absolute myth. So no, DAC is not a substitute for other forms of CO2 emission reductions. It's something else. It is complementary to other forms of CO2 emission reductions.
And I know there is quite a lot of misconception around this, because I get lots of questions about this. Why do we do DAC in the first place? It's just a way to offset fossil fuel consumption. Yeah. But you would reduce as much as possible, but you would still have that gap, 1 gigaton. And that's where DAC potentially has a role. I mean, it not potentially, it has a role.
Yeah. Yeah, and like I said, we need to go net negative second half of the century. But no, I mean, you just, any sensible person, we just start with the cheapest things first, right? So yeah. Solar, wind, maybe at some point we will put some more hydrogen in the mix. CCS is not as expensive as people think. I mean, it is also not cheap, but compared to the CO2 prices that we have currently, it can be done. Mm-hmm. So there are loads of different ways that we need to decarbonize our economy. Mm-hmm. In addition to that, we need carbon dioxide removal.
Yeah, and talking about technologies, as particularly for DAC, do you know why membranes are at low maturity level right now?
Yeah, yes, I do. Because they have only, well, I mean, by definition, because they have only been tested in the lab, so not in pilot plants. One of the difficulties with membranes at the moment is that you have to imagine that direct air capture, CO2 concentration in the air is only 420 ppms. And it may rise to 500 ppms or something like that. But that we are not talking about a separation process. We're talking about an extraction process. So you're trying to extract something from a fluid. And membranes can be very good for separations, but for extractions, maybe a little bit less, because you need a massive selectivity of your membrane to CO2 over other components of the air, like nitrogen, oxygen, argon. And then in addition, you need a very good permeability. And these two things usually tend to bite each other a bit. So either you get very selective membranes or you get very permeable membranes, but it's very difficult to get the both. So that is one of the reasons why membranes aren't considered so very much yet. They will be, and there will be applications for them, I'm sure. But that's where they're lagging behind maybe a bit.
Yeah, and you need pressure drop, and that's also volume of the gas or air that needs to be processed.
Yeah.
Couple of questions related to biological CDR or biological DAC. Is there any scope for algae-based CO2 capture bioelectrochemical process? I know what you mean. Yeah.
It's not quite my field of expertise, I have to say.
Likewise.
contrary to what most scientists and professors do, I'm not going to answer questions that fall outside of my field of expertise.
That's a good
I shouldn't
idea.
do that because I just don't know.
Yeah. I know some work is being done at on kind of macroalgae, but the capture rates are not that extensive. So it can potentially replace some of the materials, but it's not that much. We work with a company that does this. But yeah, I wouldn't comment because I don't know the specifics as well. In terms of, let's just touch on the final questions on what do you think in terms of how do we use that CO2 at the end? Do we store it for negative emissions? Do we utilize it for SAF, for example? What's your thinking about this?
I mean, if you only look at the carbon fluxes, right, in the current economy, the carbon emissions and the carbon that needs to be stored and or removed somewhere, then the vast majority of the CO2 from DAC will go stored, will have to be stored. That doesn't mean that we shouldn't use it for utilization, because it may be a very good source of carbon to make future fuels and future materials, but those volumes are much smaller. I think we have to realize that any product that we make from CO2 from the air, where at the end of life phase of that product, the CO2 is re-emitted, is not net negative, but is carbon neutral at best, and probably a bit carbon positive. What I do want to say is that it may well be that the use of CO2 for fuels or chemicals or building materials may actually initially I'm not sure if it will, but may drive the rollout of direct air capture, which allows some learning to happen and prices to come down a little bit. So it may be very beneficial to couple it to utilization. But in terms of volumes, I mean, more than 90% will have to be stored.
Yeah, because that's what the benefit of DAC is, where you get the carbon negative emissions. Cool. And there is a quite interesting question. I think we'll be finishing because we are already 10 past the hour. But last question has there been any research on the impact of offtake agreements on DAC, especially when you talk about multiple offtake agreements that can de-risk the climate technology?
This is extremely important, and I'm not sure if any research has been done on it, but offtake agreements or advanced purchase agreements and so on, they play an increasingly important role in the development of carbon dioxide removal projects, because what they do is they de-risk the project. They guarantee the investor that there be a source of income once the project has been delivered. So you're taking the market risk partially away. That doesn't take away the technology risk or other project risks, but at least the sales to an extent have been confirmed already. So I mean, I've been working with Frontier a lot, Frontier Climate Fund, and that they have done a fantastic job. I cannot, you cannot underestimate how important they have been for developing CDR.
Yeah, because you need to have that clarity of a revenue, at least to cover your basic costs.
Yeah.
Perfect. I think it's been a really great session today, and thank you all for joining. Thank you, Mijndert, for taking your time. I know you're very busy, so that's really wonderful to have you here. So the recording for the session will be available. That's really wonderful to have you here. So the recording for the session will be available. We'll make it available on YouTube and our website for Transmit. And I should have mentioned, I want to thank you to Transmit Cost Action as well for making this series of webinars happen, really. If you've got any follow-up questions, you can link to me or you can message Mijndert directly. And yeah, thank you all for joining. Hope to see you next week for the next session.
Thanks, David.
Thank you.
Good luck with the series.
Yes, it's really going well, I think. And make sure you send the feedback. So that's something I want to hear as well.
So
thank you all.
Thank you all. Good. Good weekend.
Have a good weekend. Enjoy
You
it.
too.